All right, hi students. I guess there's a maximum limit on the time on the video, so I apologize for that. Okay, so where we left off before the previous video shut down, where we left off is that we are looking at two different times that we have, the time for it to go up and time for it to go back down. Well, what we really want, if we read the problem carefully, is we want to find out. How much additional time will pass before the ball passes the tree branch on the way back down? We want to find out how much time it takes for it to go from the tree branch all the way up back to the tree branch. So that amount of time that we're talking about is delta t is 2.49 seconds minus 0.574 seconds. So delta t is going to be equal to 1.92 seconds. We will, what the problem asks us is how much time between. Let me write this better. So delta t is going to be. Sorry, the final answer is going to be 1.92 seconds. That's the time between the ball passing the tree branch the first time and then coming back to the tree branch the second time. That's what the problem is asking for. Okay? All right, so I'm going to do two more problems. They're both very interesting. So I'm going to erase this. This was, again, OpenStax 2.49. Okay? All right, so two more problems. OpenStax 2.54 is the next one I want to do. This one's quite interesting. This one says a ball is thrown straight up and passes a 2.00 meter high window. Oh, 7.50 meters off the ground. On its way up. And takes 1.30 seconds to go past the window. All right, so the question is, what was the ball's initial velocity? Okay, so this was a little bit difficult at first to think about. So a ball is thrown straight up and passes a 2.0 meter high window, 7.50 meters off the ground on its way up and takes 1.30 seconds to go past the window. What was the ball's initial velocity? So again, what's happening here? So I'll let you write this down, and I'll draw a picture. I mean, at first, this looks like an impossible to solve problem. All right, and so let me draw a little picture here now. I'm going to erase this. And so it turns out that I did this problem really in two parts. And so my picture looks like the following. Again, I have a y-axis. All my motion is going up, so I might as well just have a positive y up. And I have a ground. The ground's down here. And I can say that y naught equals 0 at the ground. And I have a window. So my window, kind of think of it like this. Here's my window. Now, the bottom of the window is 7.50 meters off the ground, as you read on the problem. So this is 7.50 meters. Okay, 7.50 meters off the ground. All right, and I'm being told that the window is 2 meters high. Window's 2 meters high. All right, and I'm also told that the ball crosses the window. As the ball crosses the window, it does so in a delta t equal 1.30 seconds. And I want to somehow figure out what V naught is with this information. So again, I have no idea what V naught is, but all I know is that the window, the bottom one, when I know the bottom window is 7.5 meters above the ground, I know the window is 2 meters high. Okay, and I know, and I can watch from inside my house or hotel room, whatever, I can watch the ball that it takes 1.30 seconds to cross the height of the window. So I may never see the person actually throw the ball, but somehow along the line, with this information, I need to determine what the initial velocity is. So the question is, well, how in the world do you do that? And the answer is you really have to divide this problem into two parts. I have to figure out the physics of crossing the window. I really have to figure out the velocity right at the bottom of the window, which would actually be the initial velocity of a problem where of just crossing a window. So what I can do is I can say, well, you know what? Let me say that there is some sort of a velocity v1 right here at the bottom of the window. Okay, we'll just say that there's I'm going to basically just look at the ball crossing the window. I don't care about what's happening below the window yet. I just want to care about the ball crossing the window at this point. All right, so ball's crossing the window. And so I'm going to go back to the equation that we've known. We said, well, okay, let's see here. I got y minus y. I'll call it y1. I'll just say this is y1 over here, right? So my y minus y1 is actually that's going to be the height of the window. So I'll say that I'll call that delta y, the height of the window. So height of window, which I'll refer to as h. So I'll say this window has a height h. Okay, so the change in y across this window, again, what the question I'm going to use? I'm going to use y minus y naught is v, I'll call it v1t, minus 1/2 gt squared. Okay, so y minus y naught is the height of the window. I'm just going to worry about the physics of the ball crossing the window, not worrying about anything below the window ledge at this point. Because I have to figure out the physics across the window. And I know that t in this case is the time to cross the window. Okay, so all I'm going to care about right now is the physics of the ball crossing the window, and I'm going to try to figure out what V1 is. All right, and so H is V1t minus 1/2 gt squared. Again, t, I know this. This is the time it took for the ball to cross the window. So I want to solve for V1. So I'm going to solve. I'm going to have V1t equals 1, it's going to equal h plus 1/2 gt squared. All I'm doing is I'm just taking V1 and putting it by itself, putting 1/2 gt squared on the other side. I'll divide both sides by t. I have V1 is h over t plus 1/2 gt. One of my t squared is one of my t's one away. All right, and so in so doing, I can now say that V1 is the height of the window, 2.00 meters, divided by how long it took for that to happen. I'm sorry, that's 1.3 seconds. I apologize. Divided by 1.30 seconds plus 1/2 9.80 meters per second squared times 1.30 seconds. If I work all this stuff out, I will find out that V1 is equal to 7.91 meters per second. Okay, so I just focused on the ball crossing the window. In so doing, I have found what would normally be my initial velocity. I just call it V1, but normally we call it V0. That would be the initial velocity of the ball crossing the window problem. Well, I will now transition to the problem of the ball leaving the ground and going to the window. So what I'm calling my initial velocity for the ball crossing the window problem is now going to be my final velocity of the initial segment of the ball leaving the ground and going and reaching the window. Okay, so I'm going to connect the two problems together. So what I've done is I can't do the original problem. I have to do another problem first. I cannot do the original problem that was given to me. I have to do another problem first before I can do that problem. So the problem I did first was the ball crossing the window, finding its initial velocity. Once I found that initial velocity of the ball crossing the window is the final velocity of the ball leaving the ground and reaching the window. All right, so it's going to kind of change roles here. All right, so I'm going to keep note of this number. I'm going to erase the rest of this. Now I want to look at a new problem, and that is the ball leaving the ground and reaching the window. New problem, ball leaving ground and reaching window. That's my new problem, okay? And so this V1, which was my initial velocity, is now going to be my final velocity in this problem. And so what I want to do is I now know that V1 is now my final velocity, 7.91 meters per second. That now becomes, it changes roles now. It becomes my final velocity. I don't know what the velocity of the ball leaving the ground is. That I do not know. I know gravity. I also know y minus y naught in this particular problem. This is the problem of between the ground and the window. Well, that's 7.50 meters. So what I could do is basically use a different equation from my catalog, one that's more appropriate. And that equation would be this one. V1 squared is V0 squared minus 2g y minus y naught. And I want V0. So I'm going to put this term on the other side. Rewrite this as V0 squared is V1 squared plus 2g y minus y naught. Okay, I'm going to put, basically all I'm going to do is I'm algebraically just moving this term to the other side to get V0 squared by itself. And now I'm going to take the square root. Square root of both sides. Again, V naught is V1 squared plus 2G y minus y naught. Put all of this under the radical. And I know everything on this side of the equation. So I'm ready to solve. And so I'm going to erase a little bit of stuff up here and just plug in numbers now. So V naught is equal to the square root of, I have 7.91 meters per second. Let's, I think it'll be all right. Minus 2, 9.8 meters per second squared times the initial height of 7.50 meters. Okay, I'm just trying to squish stuff here a little bit. All that's in a radical. So basically I'm going to take 7.91 squared minus 2 times 9.8 times 7.5. Take the square root of all of that difference. And when I do that, I find out that my initial velocity was 14.5 meters per second. That's really quite interesting. I never have to see the person actually throw the ball from the ground. All I have to do is be inside of an upstairs room, know how high the window is from the ground, measure how high the height of the window, and calculate how long it takes to cross the window. And from that information, I can determine the initial velocity of the ball leaving the ground. So it's very interesting. I never have to see the person or anything dealing with the initial velocity of the ball leaving the ground. Okay, and I want to do one more problem. All right, and so that'll be it. So again, all of these I think are very interesting. So the last problem I want to do is OpenStax 2.57. OpenStax 2.57. All right, and so what's that say? A coin is dropped from a hot air balloon. And rising. Hot air balloon. That is 300 meters above the ground. And rising at 10 meters per second. Upward. For the coin, find A, the maximum height reached. B, its position and velocity 4.0 seconds after being released. And C, the time before it hits the ground. All right, so we have a rising hot air balloon. Now you might think I'm dropping the coin, but what you're really doing is the initial velocity of the coin, even though you inside the balloon may think you're dropping it, the initial velocity of the coin is actually going to be the initial velocity of the hot air balloon, right? So it's initially going to have the same velocity of the hot air balloon, but it's not going to have the propulsion of the hot air balloon. It's going to now be a free fall particle. Hot air balloon is still going to be rising up according to the gas pressure that's pushing it up, but coin is no longer in doing that. There's nothing, so the coin is going to initially have that velocity of the hot air balloon, but it's going to then be a free fall particle. It's going to go at its highest pinnacle and it's going to come back down. But it's going to have the initial velocity. The thing to keep in mind here is that its initial velocity will be the same as the initial velocity of the balloon. All right, and so so when you say dropped, it's being dropped from the reference frame of a person riding in the balloon. But from the reference frame of a person on Earth, on the ground, watching this, this person sees, this observer sees the coin initially having a 10 meter per second upward velocity. Okay, that's the thing to keep in mind here. So what we want to do is we want to figure out, the maximum height. All right, so I'm going to erase this, and let's start working on part A. And it's a very interesting problem, and there's nuances with it. All right, OpenStax 2.57. All right, we're going to start with part A. All right, part A is going to say, okay, what's my V naught? So again, my V naught is positive 10 meters per second. It's going to be going up. The balloon is rising. My Y naught, my initial height in this problem, I'm 300 meters in the air. So initially I'm 300 meters above the ground. That's my Y naught. And I want to figure out basically what its maximum height is. So I know that at the maximum height, V, we'll call it V up. I'm rising upward. We'll call it V up equals 0. That's the important thing to keep in mind here is that at the maximum height, the balloon momentarily is at rest. Or sorry, not the balloon, the coin. The coin is momentarily at rest. All right, so out of my catalog of equations, I've not said anything at all about time so far. And so I'm going to use that one equation that has nothing to do with time. And that's going to be that V up squared equals V naught squared minus 2G Y minus Y naught. Okay, so again, we want the displacement, and that Y actually will be Y max. So that's the maximum height when V up is 0. We know that V up is 0. So we know that at this initial rising of the coin, before it begins to fall, it's when it gets to that pinnacle, when it gets to that highest point, it'll momentarily be at 0. So we're going to say, okay, we want to model the rising. So the end velocity of that rising will be 0. The initial velocity will be this 10 meters per second. And of course, gravity is causing it to come down. We want to figure out, well, what is this Y max minus Y naught? And then we really want to find Y max because we know Y naught, right? And so anyway, all right, so we want to find Y max. So first what we want to do is we want to put all of this term on the other side. And so we do that. We write, just doing algebra, 2G times Y max minus Y naught equals V naught squared. Just doing some algebra. And I'll divide both sides by 2G. I get Y max minus Y naught is V naught squared over 2G. And now I want to find Y max. And so what I'm going to do is I'm going to add Y naught to the other side. I get that Y max equals y naught, me adding y to the other side, plus v naught squared over 2g. I can plug in numbers now. Y max is the initial height is 300 meters, plus the initial velocity going up is 10 meters per second, quantity squared, divided by 2, divided by 9.80 meters per second squared. And when I do all of this, I will find that the Y max is 305 meters. 305 meters is Y max when I do that. So it's going to rise 5 meters before it starts to fall. That's what that tells me. Okay, that's the first problem, the maximum height. Okay, the second problem says I want the position of velocity 4 seconds after being released. Okay, so that's going to be very similar to like the first problem that I did. All right, and so I'm going to erase this now. Part B. So T was 4 seconds after being released. All right, so what's my equation going to be? Y minus y naught. I want position and velocity. We'll do the position now. Y equals y minus y naught is v naught t minus 1/2 gt squared. Now I'm being asked about time. And I essentially want the position, so I'm going to put y naught on the other side. So I want y, is y naught plus v naught t minus 1/2 gt squared. A little algebra there. All right, so at 4 seconds, so I have 300 meters. That's my initial position. Plus v naught, 10 meters per second times 4.00 seconds minus 1/2 times 9.80 meters per second squared times 4.00 seconds quantity squared. So that's 16 times 9.8 times 1/2 minus that, then times plus 40 plus 300. If I work it all out, y, I'll just be very specific about it, y at t equals 4.00 seconds will be 261.6 meters. So that means that, if I'm thinking about this, the initial height after the coin was released was 300 meters. And it went as high as 305. Now it's back at 261.6. That means it's falling at this point. It is now 261.6 meters. It means it is below, about 39 or so meters below where it started off. All right, and so it means it's falling. That means I expect the velocity to be negative. Should be falling. So if it makes sense, that's my initial position. So again, in my answer to part B, I would kind of just rewrite this as y of t equal to 4 seconds is 261.6 meters. All right. So now I want to find out the velocity. So again, I put the time-dependent velocity equation here, and that is v is v naught minus gt. And so v, we know the initial velocity of the coin is the same as the hot air balloon going up, minus 9.80 meters per second squared times 4.00 seconds. If I do that, then I would find out that the velocity is going to be negative 29.2 meters per second, which is exactly what I would think it should be negative. So again, my answers are going to be these two. Or if I want to be more specific, I'd write maybe v at t equals 4.00 seconds equaling negative 29.2 meters per second, to be specific about what time I'm talking about. All right. So, that's part B. Final problem of the night. I want to find out basically time before it hits the ground. So it's going to get released and then hit the ground. So we've seen a problem very similar to this already tonight. All right, so I'm going to erase this. So what I'm going to do is I'm going to define my overall position equation and ask, just like the diver, ask when is y equal to 0. All right. So part C basically says that I have y minus y naught is v naught t minus 1/2 gt squared. I want to know at what t is y going to be 0. So what t is y equal to 0, meaning that the coin hits the ground. That's what y equals 0 means in this problem, right? And so again, as you can imagine, we're going to have reemergence of the quadratic formula. So again, what am I asking? I really want y to be 0, and so I'm going to have to set up the quadratic formula. So that means I'm going to throw everything on the left hand side. I'm going to add a 1/2 gt squared on that side, subtract the v naught t. So I'm going to write this as 1/2 gt squared minus v naught t minus y naught equals 0. I got to rewrite this like it is a quadratic formula again, in that form. And so, with that said, I'm going to apply the quadratic formula. So t is negative b. Again, b is negative v naught, so negative of negative v naught, plus or minus the square root of b squared, which is negative v naught squared, minus 4. What is a? It's 1/2 g. And c is negative y naught. Okay? All this is under a radical, and everything, again, is divided by 2a. What is a? Is 1/2 g. And we've seen this a couple times already tonight. All right? So I'm going to simplify, so I'm going to erase a lot of stuff up here. All right. So t is equal to negative of negative v naught. Again, this is deja vu. We've seen this. So plus or minus square root, negative v naught, 20 squared. All of that will become v naught squared. Negative times negative back here in the second term is positive. 4 divided by 2 is 2, so it's going to be plus 2g. Y naught? And then 2 divided by 2 is 1. So all of this is divided by g. All right. And I'm ready to close it. T is going to be v naught, which we know is 10 meters per second, plus or minus the square root of 10.0 meters per second squared, plus 2 times 9.80 meters per second squared, times y naught. The balloon started way up at 300 meters. And you can always remember what problem you're doing. At the end of the day, this is a physics problem, even though you couldn't get lost into the math. Divided by g, which is 9.80 meters per second squared. When you do all that, you'll find out that you have answers that look like 10.0 plus or minus. Again, if you're doing everything in SI, you should get seconds. So again, this is going to be 100, 10 squared, plus 2 times 9.8 times 300. Once you have that whole sum, you take the square root of all of that. When you do that, you'll have 77.3 over here divided by 9.80. So again, we have two possible answers. We have 10 plus 77.3 divided by 9.0, or 10 minus 77.3 divided by 9.0. You don't want a negative time. Negative time makes no sense. So we discard the negative. So discard negative roots. It's unphysical. And so what you have now is t is 10 plus 77.3 divided by 9.8. And when you do that, you get 8.91 seconds. That is how long it's going to take the coin to be released and finally hit the ground. 8.91 seconds later. All right, that is all I want to say about Chapter 2. So yeah, it took a little bit more time than I thought, but again, you get most of the theory. You can really watch as many of the homework problems as you like. I mean, I would watch them all, but again, this is I do all this for you, so I'll give you as many examples as possible. So anyway, that's all I have for the Chapter 2.